Hello. Can someone confirm they can hear me? Nice. Okay, so I'm testing out these new earphones because I lost mine. So hopefully the sound is going to be okay. Okay, so hello everyone. Welcome back to your Comp 335 tutorial. Let me just mute that. Right. Just a reminder for anyone who hasn't done it yet, your assignment 1 is due tonight at 6 p.m. And like we sort of announced on the Moodle page, it's a lot easier for us to mark your assignments if it's in a PDF form. So if it's not in PDF form, if you wouldn't mind re-uploading it as a PDF, that would be great. Okay, so with that being said, let's get into the actual content of the tutorial. So what will we be talking about this tutorial? We're going to introduce the notion of NFAs, which you saw last lecture. We're also going to look at the NFA to Dfa conversion algorithm, which you also saw last lecture. And finally, the concept of closure properties of regular languages. Okay, so let's jump right into it. So introduction to NFAs. So an NFA, or a non-deterministic finite automaton, is similarly to a DFA, a 5-element tuple M, where the same elements are there as the ones that you saw in a DFA. So we have Q, the set of states, sigma, the alphabet, Q0 or Q0, the unique initial state, F, the set of final states, and last but not least, the famous transition function, where in this case, the transition function takes in a state from your set of states Q, as well as either an element from your alphabet or lambda. So already this is very different from what you see in a DFA, Remember, in a DFA, it was Q cross sigma. Okay, so for a DFA, this is what it was. So your delta function takes a state, right? So a state, and then either a symbol from your alphabet or a lambda, and then returns you. This is, if you don't really remember this from 232, one of the notations that you use for the power set of Q. So remember, the power set, if you don't remember, is the set of all subsets of Q. And so this is saying that delta is going to return to you a subset of Q. So in other words, your transition function will always return a set. That's something very important to remember. And it's very different from a DFA, because in a DFA, because it's deterministic, so we're already seeing this notion of determinism. When something is deterministic, you always know what the answer is. So that's why when you read a state and an element from the alphabet, you get a single state. But in an NFA, things are non-deterministic, so you're not sure what you can get if you read a state and a symbol. So that's why now it's a set, because you have an option. You may have one or actually zero or more options. So for instance, if here you had Q, reading AB went to P, and reading A went to, let's say, T, then delta Q of A would be the set P, T, right? So the set of states, okay? But because it's an FA, because it's a finite automaton, the actual input and output of an NFA remains the same as a DFA. So that is, you can think of an NFA as this black box where you give it an input string. So you give it an input string W. It takes that input string, does some computation, going through some states, yada, yada. And then either you end up in a non-final state, in which case you reject, or you say no, or you end up in a final state. And it's not like a DFA where you end up in a final state and that's it. You have to end up in the final state, and W has to be completely red, okay? And in that case, you'll have an accept or a yes. And so just a quick aside of what I mean by this, because your string lands in a final state, it doesn't necessarily mean that your NFA accepts it, because your NFA has to land in a final state and has to completely finish the input. So for example, if you have WAAB and you have the NFA that goes from Q0 to Q1 with an A, and from Q1 to Q2 with an A, and Q2 is a final state, then if you read this string in this NFA, then you'll read this A, you'll go to 1, you read this A, you'll go to 2, then you read this B and you won't have anywhere to go. So you could say that you stay in the final state 2, but the input is not completely read. And so because the input is only partially read, you would reject this string. Okay, so that's the sort of high-level view of what an NFA is. Now, if we get into the more sort of mathematically rigorous definitions, so like I said before, if we're given a string W, what M tries to do is it tries to sort of do an exhaustive search of all the possible walks of your NFA. And if at the end, in any of those searches, you end up in a final state and you finish your full string, then you say that the string is accepted, right? So if in any of those walks you end up in a final state, but if in all of those walks you don't end up in a final state, or you don't finish the input string, then your string is rejected. Okay? So very much like a DFA, we have the sort of concept of the language L of M, the language accepted by the NFA M. And so it's again a set of strings that for each of those strings can have a computation where the string is completely finished and they end up in a final state. Okay. And so if you want to think of it a bit more formally, you can think of the language accepted by M as the set of all strings that belong to the set of all strings in your alphabet, such that when you read the transition function starting from Q0 and reading the input W, you have at least one final state in your extended transition function, okay? So the extended transition function is very similar to the one from a DFA, where instead of just reading a symbol, you read a string. And so this tells you, so delta star, let's say Q0 AAB, tells you the states where you end up in when you read, states you end up when you read AAB in your sort of NFA. Okay, so hopefully this is more of a review for everyone. This is sort of something that I think you can just read on your own. It just shows some of the differences between DFAs and NFAs. To be honest, it'll be clear just by doing examples that these are things that are going to come out. So I'm not just going to mindlessly read them. But now let's look at an actual example. So we have an NFA here. So first of all, why do I say that it's an NFA? Because if my alphabet is A and I have this state Q0, Q0 is an over-specified state, because instead of having exactly one edge that corresponds to the symbol A, it has two edges that correspond both to the symbol A. And so it means that when you start at Q0 and, for instance, you read an A, you have a choice. So that's why it's non-deterministic, because there isn't a fixed answer for what happens when you read A in your NFA. Okay, so you have this NFA, and we're going to sort of trace some inputs through this NFA in this example. Okay, so the first input string that we're going to look at is going to be AA. Okay, so remember, your NFA is going to accept the string if any of the walks, so if any of the paths that it takes reading AA lead to a final state. And of course, it needs to finish that input string. So you can kind of tell that there's only two possible walks in this case. If you start with AA, you're going to, of course, always start at Q0. So you start at Q0. You can either go here, reading an A, so you read an A, and you get to Q1. But now you're at Q1 and you have no transitions. And so even though you end up in a final state, it's not because of this path that you're going to end up accepting AA. So this does not lead to an accept. Okay, so this path doesn't lead to an accept. So let's try the other one. Again, if we start at Q0 reading AA, so we're going to read this first A and go to Q2. Then at Q2, we're going to read this other A and go to Q3. And now I've finished. So my input is finished. So that's the first thing. And the second thing is I end in a final state. And so because of 1 and 2, because 1 and 2 are both satisfied, then this means that AA is accepted. Okay? And that's how you would read an input that would be accepted by your NFA. So, right, so here, like I said, one of the possible walks ends in a final state, and it should say here, and the input finishes, right? So it's completely read. And so because of that, M accepts the string. So if we look at an example of a rejection, I'm going to go over this a bit quickly because it's going to be the same mechanism. We have in this case A cube or AAA. So we know that if we go through this path, we're going to be at Q1 and we're going to be reading this A. But when you're at Q1, you have nowhere to go. So in other words, if you have delta Q1A, this actually gives you the empty set, right? Because you can't go anywhere. But because you still have input to read, this means that this path is not going to lead you to an accept. And then if we go through this path, so if we read this A and we go to Q2, this A and we go to Q3, this A and we go back to Q2, in this case, we didn't end up in a final state. So this is not final. And so because in this case, we just don't end up finishing the inputs, and in this case, we don't end up in a final state, we've essentially done all of the possible walks, and in all of the possible walks, we don't get to a final state finishing the input. And so M, the NFA M is going to reject this string. And so just FYI, what is the actual language accepted by this NFA? Well, we see that if we have just one A, right? If we have one A, then we can take this path to accept it. And then if we have two A's, we know that that gets accepted through here. We know that three A's don't get accepted. Then four A's will get accepted because here we're at AA, and here we're at AAA, and then here we're at AAA, right? So A4. So in other words, we have all of the even length A's union a single A, okay? And so this might have been very annoying to write in a DFA, but it's quite easy to do for an NFA because your NFA is going to try all the possible paths, right? It's going to do like an exhaustive search. And so we can just sort of put all of the machines that correspond to each of these languages together, and our NFA is going to end up accepting one of them, okay? Or using one of them to accept the string. All right, so now let's do an exercise. So we're given the following NFA M, and we want to know what states do we get when we read 0, 1, starting from Q0. So I'll give you 1 minute to try this out, and we'll look at it together. Okay, I think I should intervene. Okay, this one is a bit tricky. So let's try it out. Okay, so we have 0, 1 as the input strings. So what are the states we can reach with 0, 1? So let's see, if I start at Q0 and I read this 0, right? I can read this 0, then I go to Q1, okay? Then what can I do? Well, here what I can do is I can use these lambda connections, right? A lambda connection doesn't cost anything, so I can just use it to skip to the next state. So let's see, I can from Q1 for free, so at the cost of not reading anything, so at no cost, free of charge, I can go to Q2, okay? And then from Q2, then I can read this 1 and go back to Q1. Okay, so I know that I can reach Q1. Another way actually that you could have thought of this was 0, 1 is the same as 0 lambda 1, right? So then you could have also said, okay, I start at Q0, I read this 0, right? Then I read this lambda for free, and then I read this 1 going back to Q1. Okay, so that's the first one. Then what else can I go to? So if I read a 0, so I have no choice in this case to start reading a 0. I can again go back to Q1. Then I can, let's see, what else can I do? I can, yeah, okay, good. So then I can, so 0, 1, so I have a 0. I can use this lambda again for free. Okay, so using the lambda again for free, then using the 1, so I'm back to Q1. Then I can use the lambda here for free to go to Q0. Okay, so I can go to Q0. And the other one that I can do, so if I have 0, 1, yeah, the other one I can do is if I start at Q0, so I can read this 0, go to Q1, then read this lambda for free, go to Q2, then read the 1, go back to Q1, and then read this lambda and go back to Q2. So I would use, again, 0, lambda, 1, lambda, but this to go to Q2 and this one to go to Q0. So in fact, here I actually can reach all of the possible states, including Q0, which is a final state. It's a final state. And so that means that 0, 1 is accepted. So this one, I agree, was pretty tricky because I see some of you said not accepted. Could you also just bounce between Q0 and Q1? Bounce between 0. Yeah, you could also do that. Yeah, so yeah, good, very good. So what Nabil is saying is you could read a 0 here, so you could go here, and then you could bounce, so read this lambda for free, then read this 1, go to Q1, and then read this lambda for free and go back to Q0. Yes, very good. So so this is why you have to be, I'll write in capitals, very careful of lambda, okay? Because if you just ignore the lambdas or you kind of use them, then you can get into a trap like this, okay? So so I think this was actually a pretty good exercise. Okay, so that's the answer. So yes, it's accepted. Now, a different type of exercise is NFA creation. So again, I think we're actually not doing that bad on time. I'll give you another minute. This one I don't think is that hard, so try it out and we'll see what everyone gets. Well, we won't see, but you know what I mean. Okay, so let's say it's been about a minute. What was the trick here? Well, the point of this exercise was kind of to emphasize the point that I made for the first NFA that we had saw, where essentially when you have a union of these types of languages, you can just create, so let's say L1, L2, L3, you can create NFAs or machines, let's say M1, M2, M3, such that, let's say, MI accepts LI. So you create each of those machines, M1, M2, M3, and then you create a new initial state, and you connect, you lambda connect each of these, okay? And because, again, lambda allows you to go to somewhere for free, right, free of charge, then, and because this is non-deterministic, then if you're given a string, any string, what's going to happen is your machine is going to say, okay, I'm first going to try M1, see if it accepts it. If no, then I'm going to continue to M2, and if it doesn't get accepted, I'm going to continue to M3. And if at any of those points you do accept, if any of those machines do accept, then you just return a yes. Okay. So how do we do that? How do we build each machine? So I'll already connect these with lambdas, like so. So machine M1 is just B. So I can just say, I just want the string B, right? So notice I'm not adding an A, right? I'm not adding an A here. I don't need to add extra transitions here because this is an NFA, right? So it's allowed for it to be underspecified. So it's allowed for there to be missing transitions or for there to be lambda transitions, okay? The next one is AB to the n for n strictly greater than 0. So it means that I need at least one AB, right? So I need to start with AB and then have any number of ABs, so for n greater or equal to 0. So that means that I need to read my first AB, then I can already accept, and then I can do this kind of AB loop. So I read an A, and then I read a B, and then that's going to give me a bunch of consecutive ABs, right? And again, notice how I'm making my life a lot easier than with an NFA, than with a DFA, because I don't need to specify each transition for each state, okay? And then the last one is W in AB star for the length of W mod 2 equals to 0. So in other words, even length strings. And so hopefully by now we know what the typical FA for even and odd length looks like. So this is going to be your even state. And then if you read ABs, you'll go to your odd state. And if you read an A or a B, you'll go back to your even state, okay? And so this would be an NFA to accept this language. So maybe a question, do we have a quick, yeah. So maybe a quick question for you is, how can I easily reduce? So I'm not talking about like DFA minimization. How can I easily reduce this NFA to have a smaller number of states? So I'm going to leave this question for you. And so think about it a little. And if you want to know the answer, just let me know. Okay. So that's for that exercise. And I think that's for the section for NFAs. So any questions regarding NFAs before we go to the conversion? No, doesn't look like it. Okay. So the next topic that we're going to do is the NFA to DFA conversion algorithm. Conversion algorithm. So You've already seen it, but and I'm actually not gonna, so I'm not gonna really read through this, but the basic idea, right? What's the basic idea? Is that an NFA just allows you to have more than one choice for different states. And so the idea to convert it to a DFA is to list out all of those possibilities, right? So to sort of expand out all of those possibilities, and what else? And then make each decision. So for each state, make it a deterministic decision. So where you have exactly one choice. So that's the idea, right? And so you can go from an NFA to a DFA using an algorithm. And so how do you go from a DFA to an NFA? Well, that doesn't, you don't typically do that, right? Why? Because actually a DFA is already an NFA. Okay, why? Because a DFA is just an NFA that doesn't use non-determinism. So it's as if the NFA had this power, but it just never used it, right? And so that's why all the DFAs are NFAs. And with this algorithm, we're going to show that every NFA can be converted to a DFA. And so in fact, what this is going to show through this process, what we're going to show is that the languages, so this you've also already seen in lecture, but just to remind you, the languages accepted by DFAs are in fact the same as the languages accepted by NFAs. So the set of languages are the same, the family of languages are the same. And so in the end, what does this tell us? This tells us that to prove that a language L is regular. So remember regular languages, to prove that a language is regular, for now, all we could do is create a DFA that accepts it. But now we can do, the first thing we can do is create a DFA M such that LM is equal to L. Or now, because we know that DFAs and NFAs are equivalent in power, right? They have the same computational power. Then what we can also do is create an NFA M such that L of M is equal to L. And both of these will allow you to prove that the language is regular. Okay, so this is an aside that I was going to talk about after, but this actually gives you a good motivation of why we care about the conversion algorithm in the first place. So it's because it enables us to do this, to have this second choice. Okay, so quickly, let's just look at it quickly. What are the steps to the algorithm? So the algorithm always starts by creating a initial state Q0. So you always start with the initial state Q0. Then from the initial state Q0, find all of the states that can be reached from that initial state. Then each of those sets of states become a state in your DFA. Okay, and then you repeat this step. For each of the states that you found, sort of continuing to see what's the set of states that go out from the states that you just found, right? So it's a very recursive algorithm. And then at the very end, you essentially stop when you have no more new states that appear, okay? So you stop when you have no more states that appear. And for your final states, right? So the final states of your DFA will be all of the states that have final states in your NFA, okay? And lastly, if your original NFA accepts lambda, then make the initial state a final state. So that probably doesn't make any sense to you. It probably doesn't even make sense to me right now. So that's why we're going to look at an example, because that's the best way to understand an algorithm. So we're given this NFA M, and we want to convert it to a DFA M prime. Okay, so how do we do that? Well, I think you already know the classic table that we write. So we write the classic sort of states that are going to be created here. And now we write each of the symbols of your alphabet. So in this case, the alphabet is 0, 1. So I want to know what are the possible states that I can go to from each of my states that I'm going to discover. So in the algorithm, you initialize it by starting with the set Q0. So what do I do from here? I ask myself, from Q0, where can I go when I read a 0? So if I read a 0, I can go back to myself. So I can go to Q0, or I can go to Q1. And that's about it, right? So those are the only two states I can reach from Q0, reading a 0. What about 1? If I read a 1, I can only go back to Q0, right? So this state I already know, but this is a new state, and so I'm going to add it to this column, and then repeat the same process of discovering states, okay? So Q0, I know that when I read Q0 from, when I read 0 from Q0, I get Q0 and Q1. The fact that I have this extra Q1 doesn't help me, so that's about it. Then for one, if I'm in Q0, I can read myself. So I go back to myself if I read a 0, if I read a 1, sorry. So I can list Q0 as one of the states, and I can also list Q2, right? Because the fact that I have Q1 in this set means that from Q1, when I read a 1, I go to Q2. Okay. Next, so this guy is already here, but this guy is a new state. So I'm going to add this new state. Okay. And so the same process happens. From this Q0, if I read a 0, I can get Q0 and Q1. From Q2, I can't read anything, so that doesn't help me. Then if I read a 1 from Q0, I get myself, and from Q2 I get nothing, and so that's it. That's all I get. And so I don't have any new states, and so that's about it. That's all the states that I can create for my DFA. So now it's time to actually map these states to an actual DFA. So how do I do that? So the initial state is always going to be the state that contains the set that has the set only of Q0. So this is always going to be my initial state in the conversion algorithm. Okay. Next, I have Q0, Q1, and I have Q0, Q2. Okay, so the next thing I do is I just read for each symbol what the state I end up in when I read that symbol, right? So if I'm in Q0 and I read a 0, I can go to Q01. And notice that this choice is now deterministic. It's deterministic because what I've essentially done is I've listed all the possibilities inside the actual state. So that's the idea of the algorithm, is just list all the possibilities in the state of your DFA, okay? So that's what happens when I read a 0 from Q0. Then when I read a 1, I just go back to myself. Then if I'm in Q0, Q1, if I read 0, I go back to myself. If I read a 1, I go to Q0, Q2. When I'm in Q0, Q2, I read a 0, I go back. Oops, I didn't write the symbol here, the transition. If I read a 0, I go back to Q0, Q1. Then if I'm in Q0, Q2, and I read a 1, I go back to Q0. So if someone is saying something, then I make a mistake. Don't think so. Yes, someone unmuted yourself. I can hear you. Oh, no, you're. Okay, this was a mistake. Okay. So I think it's good. I don't know, Dominic, if
Oh, sorry. Yeah, isn't there Q0 to Q0? Q0 when you see 0, you go to Q0, but on the bottom there's like it says Q0, Q2. You didn't make it go there.
this one. Which one don't you think
Wait,
goes?
no, sorry, never mind. Okay, I read something wrong.
Okay. All right. Okay, no worries. No worries, it's all good. Okay, question. So any state containing, yes, very good. Okay, so I wasn't done, right? Now the last step is my final states. So the final states in my DFA are any states that contain final states in my NFA. So in this case, the final states in my NFA are only Q2. And so the final states in my DFA are going to be all of the states that contain Q2. And so in this case, it's just this guy. So this guy will be a final state. For Q0, Q2, for A does not go to, for a 1, okay, for a 1, Q0, Q2. When you're, so Q0, Q2, right? When you read a 1 and you're in Q0, you read a 1 and you go back to yourself. So that's for when you're in Q0. If you're in Q2 and you read a 1, you don't go anywhere, right? So delta Q2 1 is empty. So then together, you only go to Q0. Okay. Any questions about this example? No, okay, doesn't look like it. Okay, so there is, in theory, an exercise here. Trying to think how relevant it is for me to do it. I think, yeah, okay, so I won't give you time to do it, and I'll go over it rather quickly, just for you to sort of, because the answer here is actually after minimization. So if you do it on your own, then maybe you won't get this, and then so maybe it's actually worth it if we do it together. Okay. So if you want to follow along, that's cool. That would probably be useful for you, but I'm not going to give you some extra time to do it. Okay. So we want to convert the following NFA into a DFA. So again, we have 3 states, but now the first thing that I notice here is that I have a lambda. So I have to be very, very careful about this lambda. Okay, so I set up my table. Let's make this proper. So state A, B, this. How many states do I have? 2. Okay. 2, 4, 6. All right. All right. So I set up my table, and now as usual, I start with Q0. Right. So if I start with Q0 and I read an A, what happens? So a question for you. So if I read an A from Q0, is it the empty set? Okay, good. Very good, okay. Okay, so is it just Q2 and just Q0? So someone is saying it's Q2, someone is saying it's Q0. Yes, okay, someone is saying it's the union, and it is in fact the union. Again, let's just look why. Remember, the lambda you can use for free, right? You can do whatever you want with the lambda. So if I'm in Q0, I can go to Q2 for free. Then I can read this A, go back to Q0. So that's where the Q0 comes from. But then I can again use this lambda to go back to Q2 for free. Okay. And so that's why it's the union. So it's Q0 and Q2. Okay.
I have a question. If
Yes.
there wasn't the arrow going from Q2 to Q0 with the A, if it was just a lambda, could we still include Q2 in that case?
That's a good question. What do you think?
I think so.
So remember, you can, when you read the lambda, right? So imagine you have an A, right? And you're reading this lambda. It means that your pointer is now moving, right? So if your pointer is now moving and you end up in Q2, right? That means that you haven't read A yet, okay? So it means that you haven't actually used the transition A.
Okay, so you wouldn't include it actually.
Yeah, exactly, yeah.
Okay, cool.
But that's a good question. So you really, for it to be included, you really actually have to go through A exactly once in this case. Okay. So, okay, nice. So we've established that it's Q0 and Q2, and immediately I can actually add it here because I know it's not already in my states. So I can do that. And then for B, it's not, there's no danger because I can see that my B only goes here and there's no B's involved to the right. So I can just write Q1. And both of these I haven't seen before, so I can add both of them. Okay.
Sorry, it was a continuation to my previous question.
Mm-hmm.
In that case, if A needs to be consumed, how is Q2 included from Q0 to
Yeah, it's a good question. So so remember you have your initial symbol is A. So you can go to Q0 by doing lambda, right? Lambda A, right? But then you can add an extra lambda at the end to go back to Q2. So you can do lambda A lambda, and this is still going to give A, right?
Yeah. Okay.
So that's why. Good.
Sorry.
Yes.
Sorry?
Yes.
But when it is in Q0 and when you give a, should it go to the, if there's no lambda path and you give it an A, so should it go to an undefined state? If there's no lambda.
If there's no lambda.
Yeah. So
okay,
then you give it A.
Yeah. Then you have no states, right? So then it's the empty set.
You go to a new state, right?
Yeah, it would be the empty set, and the empty set becomes a state, and then by default, this always goes back. This always goes back to itself.
Oh, okay, thank you.
Okay, no problem. I think we might actually get an empty set, so that'll be good. Okay. So so we have these two new states, Q0, Q2, and Q1. And again, we're going to repeat the same process for both of them, right? So for Q0, Q2, when I read an A, I know that for sure I'm going to have Q0 and Q2. Can I get Q1? That's the question. So from Q0, I can't get Q1. From Q2, I can't get Q1. So no, that'll be it. Then if I'm in Q0 or Q2 and I read a B, if I'm in Q2 and I read a B, that doesn't help me at all, right? Because this is an A and, oops, sorry, and both of these are ingoing edges. So that doesn't help me, or incoming edges. So the Q2 is not going to help me to get anything from B. Q0 is, though, it's going to allow me to go to Q1. And that'll be it, actually. So in fact, Q0 and Q0, Q2 are going to actually do exactly the same thing. And so if you watched the, so quickly, actually, let me answer that question. Nabil, Q1 is a new state because it hasn't been read in this column here. So as soon as you see something that's not above what you're doing, then you add it as a new state. Okay, but just as I was saying, these two states, they do the same thing. And so if you watched the minimization tutorial, the extra tutorial, then you can already think that when you do the minimization algorithm, these two guys would actually go together. But that's not really the purpose of this exercise. It's just an aside. Okay, so this hasn't added any new states. So now we're going to go to Q1. So when we're at Q1 and we read an A, what can happen? We can go back to ourselves to Q1, or we can go to Q2. We can't skip this, go to Q2, and then go to, like, we can't go to Q0. There's no way to go from Q1 to Q0 reading an A. So that's all the states that we can reach from Q1 when you read A. Then when you read B, so if you're in Q1 and you read a B, you can go to Q2, and that's it, right? So you can go to Q2. So we have two new states. So we have Q1, Q2, and we have Q2. And we're going to, again, do the same process, right? So from Q1, Q2, let me erase this. From Q1, when you read an A, I know that I can get Q1 and Q2 just by kind of looking at this, right? So I just paste this. I'm going to maybe potentially add some stuff. So from Q2, if I read an A, so if I read an A, I go to Q0, then I use, oh, okay, then I can just stop at Q0. So then I add a new state. And that's it, right? I'm not going to add more states than the ones that I have in the NFA. So that's for when you read A. Then for when you read B, if you're in Q2, so remember, if you're in Q2 and you read a B, that doesn't help you at all, right? But if you're in Q1 and you read a B, you can go to Q2. So you get Q2 out of this. So this state is already seen. This is a new state. So I'm going to add it here, Q1, Q2, Q0. Okay. So then so now let's do Q2. So once we're in Q2 and we read an A, then we can go to Q0, right? So we can go to Q0 with the A, and then we can hop on the lambda for free and go to Q2. What about when I'm in Q2 and I read a B? So what do we think happens when I'm in Q2 and I read a B? What states can I go to? Empty set, yes, very good. So from Q2, this doesn't help me in reading a B. These are incoming edges. And so the set will be empty. So I get this new set. So this set is already seen, but this one is new. So I'll add it. And so actually, this one is fast to do. If you have the empty set, you always go back to yourself because there's no states, right? Next and last, Q0, Q1, Q2. When you read an A, well, put it this way, when you have Q1 and Q2, you know that you read all of them And so I know that I can just say when I read an A, I read all of them, right? I can't do the same thing for B though, I have to be more careful. So when I'm in Q1 and I read a B, I can go to Q2. When I'm in Q2, I can't go anywhere. When I'm in Q0, I can go to Q1. So I get Q2, Q1 or Q1, Q2. So this one's already there and this one's already there. Okay, so I'm done this process. So now all that's left is just creating the actual DFA, right? So, so let's do that. So I have Q0, Q0, Q2. How did I organize this? Okay, actually, let's do it like this. Q1 is here. Q2 can go here. Q1, Q2. Put the empty set here. And Q0, Q1, Q2 here. All right, so you set up the states. Q0 is always the initial state. And then you just read the transitions as if this was the transition function for a DFA, because actually that's what it is, right? So when you read an A, you go to Q0, Q2. When you read a B, you go to Q1. From Q0, Q2, when you read an A, you go back to yourself. And when you read a B, you go to Q1. When you're in Q1 and you read an A, you go to Q1, Q2. And when you read a B, you go to Q2. When you're in Q1, Q2, and you read an A, you go to the set of all states. And when you read a B, you go to Q2. When you're in Q2 and you read an A, you go back to Q0, Q2. When you read a B, you go to the empty set. The empty set is a trap state. And what else is left? Q0, Q1, Q2. When you read an A, you go back to yourself. And when you read a B, you go back to Q1, Q2. Okay. So yeah, so that's it. So that's your DFA. And that would be the result of your algorithm. So you can kind of see that here I have, I ended up with 7 states. And then if you would minimize it, you would get maybe less states. But now maybe a question, another question for you is, what would be the minimum and maximum number of states when converting an NFA, which has a cardinality of the alphabet is M and cardinality of the states is N. So when converting this NFA to a DFA. So what would be the minimum and maximum number of states? All right, I didn't do that. Yeah, final state, sorry, thanks. Thanks for reminding me. So I actually didn't finish this. What would be the final states here would be all the states that have Q0. So it would be this guy, and this guy. And you explain the final states in the converted DFA. Yeah, so the final states in the DFA, right? So a state is final in the converted DFA if, so suppose you have a final state, let's call it S. Let's call it just S, right? So you have a state S. So let me start over. Sorry. So otherwise you're going to get confused. So suppose you have a state S in the converted DFA, right? Then S is so belongs to the final states if there exists a final state in the NFA that's also in S. Okay, so what is this? What is this saying? S is a final state in your DFA if it contains at least one final state in your NFA. So for instance, Q0, Q2 contains Q0. Q0 is a final state in your NFA. And so in your DFA, it's a final state. Okay. Can you explain Q2 when you read B goes to, yeah. So Q2, yeah. So if I'm Q2 and I read a B, so, well, what are the possibilities, right? So I'm in Q2, I can't use this edge, right? This is an incoming edge. So that's no good. I can't use this edge either because it's also incoming, right? And I can't use this edge because the transition here is for an A, right? So I have essentially for B, I have no possibilities. So then that means that if I have no possibilities, then my set of states is empty. So that's why Q2, when you read a B, gives you the empty set. Yeah, no worries. Okay, so so maybe just think of this question. Again, I realized that doing questions at the beginning of the tutorial makes the tutorial last 30 minutes longer. So I might not answer it at the beginning of the tutorial, but think about it. If you want to, actually think about it, don't just ask me for the answer. And if you think about it a bit and you get stuck, or if you want to confirm the answer, then just let me know. Okay, so there doesn't look like there's questions for this. This is basically just what I said before, that using this algorithm, we've shown that DFAs are equivalent to NFAs in the sense that they accept the same languages. And so the languages accepted by DFAs is equal to the languages accepted by NFAs. And so to show that something is regular, you can either create an NFA or a DFA. Okay. All right. So if there are no questions, I'm going to go to closure properties. Okay. So closure properties. So closure properties of regular languages. What does this mean? So first of all, let's have just a quick reminder of regular languages. So as I just said before, languages accepted by NFAs is equal to the languages accepted by DFAs. And a language is regular if and only if. So by this theorem, a language is regular if and only if an FA. So sometimes you might see this. So this is actually important for you to notice. An FA, so when you see this in the assignment or in any other type of evaluation, an FA can either mean an NFA or a DFA. So if it says something like an FA can have this kind of transition, so it can have a lambda transition, then this is true. Because an FA is either an NFA or a DFA, and an NFA can have a lambda transition. If this was a DFA, then it would be false, because DFAs cannot have a lambda transition. So that's just terminology that you should just be aware of, because it's kind of easy to trick students with that terminology. So the idea of closure properties is if we have the knowledge, so if we know that L1 and L2 are regular, and these two languages are combined with some language operator, then can we conclude that the result of that language operator is regular? Okay, and that's where closure properties come in. So if we have two regular languages, L1, L2. And L1, just so this might be confusing. This might be confusing because it's a theta. Just think of it as L1 operation L2. If L1 operation L2 is regular for any L1 for any L2, then we say that regular languages are closed under this operation. So what do I mean by that? Well, for example, if I have two arbitrary regular languages, L1 and L2, then I know that their union will be regular. So you've already seen the proof for this, but a quick reminder, I'm not going to do it for all of them, but just for this one, we already kind of did it when we solved the DFA, the NFA in the exercise. So if L1 is regular, right, what does it mean if L1 is regular? That means that there exists a machine, an FA M1 that accepts it. The same thing for L2. So we have machines M1 and M2 that accept L1 and L2 respectively. So we have these two machines. So now what we can do is we can create a mega machine that accepts L1 union L2 by using lambda transitions, right? So we can just say we create a new initial state, create this lambda transition to M1, this lambda transition to M2. And then if I have a string W that belongs to L1 union L2, then either it belongs to L1 or L2 or both. So if it belongs to L1, it's going to go through M1 and then be accepted. If it doesn't belong to L1 but belongs to L2, then it's going to go to M2 and get accepted. And if it doesn't belong to either, then both of these are going to reject it, and then W is going to be rejected. Okay. And then actually, it's the same idea for all of these kind of standard, except maybe for these two. For these, you can just use lambda transitions to kind of concatenate the boxes together so that this big box that represents this big FA accepts the sort of result of the operation of those languages. So that's why, for instance, the concatenation gives you a regular language, the clean star closure gives you a regular language, the reversal gives you a regular language. That one just works by reversing your directions and changing. So actually, let's do that one. So if L1 is regular, then it has a machine M1 that accepts it. So think of this machine M1 as so. So we need an extra step for this proof. So we know that we have a single initial state, but we could have multiple final states, right? So we could have a final state here, final state here. So the idea for this proof is that you're going to not make these final, you're going to make these non-final, and then connect them with lambda transitions to final states, to a single final state. So then what this tells us is that any FA can be converted to an equivalent FA with only one final state, right? So notice that I said any FA. Yeah, so it's any FA because for a DFA, you could use the sort of NFA to DFA algorithm, right? And then bunch up the final states together. And if it's an NFA, you can just use this trick here, okay? So that's the setup, right? So you have a machine M1 that has a single initial state and a single final state. And then the trick is just to reverse. So you reverse all of the transitions. So let me do that in a different color. Reverse all the transitions. Make this your initial state. Make this your final state. And then make this not final. Then this becomes the machine M1 prime, where M1 prime is going to accept L1 reverse. Okay. So that's the proof for L1 reverse. L1 complement, we've already seen it. That's the one where you swap final states for non-final states and vice versa. The intersection one, that one's a bit more complicated. You can just sort of, you'll see the proof in lecture. Then there's another useful one, which is the homomorphism. So what the heck is a homomorphism? It's just a function, so it's a mapping that takes symbols and gives you sort of a symbol. So this just says that if I have the symbol A, then I return the symbol A, and then if I have the symbol B, then return the symbol B. Let's actually change that to A. So let's say you have this function, okay? And so if you apply H to a regular language L1, so what does that mean? That means that for each of your strings in L1, you're going to apply H to W, right? So for all of those strings, then this language will also be regular, okay? So that's what it means for the homomorphism, for regular languages to be closed under homomorphism. Okay. Next, we have a property that says that if L1 is finite, then it is regular. So this is always true. And the reason for that, so why is this true? Because imagine you have L1 is, so you have a finite number of strings, right? So you have W1, W2, until Wn. Then you can create an NFA that looks like lambda, and then the machine that accepts W1, lambda, the machine that accepts W2, and then so on, lambda, the machine that accepts Wn, right? And then this gives you a machine that accepts L1. So all finite languages are regular, right? And last but not least, what about L1 different L2? Do we think that languages are closed under this property? Regular languages, sorry. Well, no answer means I've lost someone. Okay, so suppose you have L1 is regular and L2 is regular, then is L1 different L2 always regular? No. So maybe a hint, there's an alternative way of writing the difference, right? Which is what? It's L1 intersect L2 complement, right? So L2 is regular, right? So L2 complement, this is also regular because of this property here, right? L1 complement is regular. And L1 is regular, right? So I have two regular languages. When I intersect them, because of this property, ooh, this is a mess. Because of this property, L1 intersect L2 complement is also going to give you a regular language. Okay, so regular languages are also closed under the difference operator. All right. So why is this useful? It's useful when you have a question like prove that a language or disprove that a language is regular. You can use the closure properties to use smaller languages as building blocks. So for example, if you wanted to show that AN, BN for N, M greater or equal to 0, so show that this is regular. So we know two ways of doing this already. The first way is a DFA, right? Create a DFA that accepts a language. The second way is an NFA. But now we have a third possibility, which is to use closure properties. So use closure properties. So how would we do that? Well, we could say that we could split this language into two. So let's say L is my big language. Then I could have the language L1 is AN. n greater or equal to 0. L2 is bm for m greater or equal to 0. Then what? Then I know this is regular because I can create this NFA that accepts it. And I know that this is regular because I can create this NFA that accepts it. So L1 is regular, right? L2 is also regular. So then because of this property, right? Regular languages are closed under the concatenation. L1, L2 is regular, which is equal to AN BM for m greater or equal to 0. But I know that by the sort of concatenation operation, this is going to give me AN BM and comma n greater or equal to 0. And so what does this mean? This means that this language is regular. So that's another way of proving that AN BM is regular. Okay. So now an example is the language L ANBN for n less than 335 regular. So question for you, is it regular, is it not regular?
Regular.
Yes, very good. Excellent. It's regular because this is n less than 335. Yes, it will. It will definitely produce a massive NFA, or an even bigger. Actually, imagine trying to make a DFA with this. That would be well, yeah, it would be a bit tough. So yes, it is regular. Why? Because L is finite. Why is it finite? Because n is strictly less than 335, and so L is actually lambda AB all the way to A334, B334. So it has 335 elements. So it's clearly finite, and so because it's finite, it is regular. So I'm happy someone asked this question. What about AN BN for n, let's say greater or equal to 335. Okay, so is this going to be regular? So you might not have seen this actually, or maybe he did show you this, but the short answer is this is not regular. So this is not regular. And actually, this is a very, very, very famous sort of non-regular language that you're going to see very, very soon, because it's kind of the building block for why we can't just stop the course at NFAs and DFAs, and we need something more powerful to accept a language like this. So this language is not regular. So what does this mean? This means that there does not exist a DFA or NFA that accepts it, right? Because if it did, then sort of by definition that would mean that it was regular, but it's not regular. And the intuition behind this, how do you write? Okay, the intuition behind this is that. So that's a good question. I'm going to get to that in a second. So the intuition behind why this is not regular is because it requires memory. Okay. So what do I mean by that? Because if you want to accept AN BN for n greater or equal to 335, and you don't know what the n is, right? You don't know what the n is. So that means that you need to remember, you need to keep track of how many A's you have. So you need to count the number of A's, right? You need to count the number of A's. And that's not something an FA can do, right? That's not something an FA can do because an FA has no memory, right? the last thing it remembers is what it just saw. It doesn't have the power, it doesn't have the computational power to remember the number of A's it saw. And so that's the intuition behind why it's not regular. And you're going to see a more rigorous reason in the lecture, in a couple of lectures, when you look at the pumping lemma. Okay, so before we do this one, there was a good question. Can the union of a regular language and a not regular language be regular? You see, so this is a Kalman trap, and this is why I said that sigma star, the empty set, and the language containing lambda, are the most important languages to remember, especially when you do a question like that, especially when it's a true-false question, and it's something like that where you need to either find a counterexample to disprove it or prove it by a proof. But generally, if you want to show that something is not true, these are going to be the languages that are going to help you do that. So here, can the union of a regular language and a not regular language be regular? So sigma star is regular, right? I hope everyone knows that. Why is sigma star regular? Because this is an FA that accepts it, right? So you have a regular language, and now let's say you take the union with a non-regular language. So let's say AN, BN, and greater or equal to 0. This is non-regular, right? But sigma star is the universe. So the universe union anything gives you the universe. So this gives you sigma star. Sigma star is regular. So can the union of a regular language and a not regular language be regular? Yes, it can. And this is the reason why, okay? Because there is such a language. And actually, that was going to be one of the questions, so that's good time. So as I said, really remember to try to use these whenever it's a quiz question like that or a test question like that, because those are going to be really useful for you to try to disprove or try to find an example. Okay. Okay, so maybe let's leave that discussion for AMBM. Okay, so Nelson, no. Right, the answer to that is no, because right, these are this language, right, L is the set of all strings that start with a bunch of A's and then finish with a bunch of B's, right? Sigma star is literally the set of all possible strings over sigma. Okay, so
sorry,
very
may I ask a question?
Yes, go ahead.
I know this is related to the quiz, not to the tutorial itself.
Okay.
On the quiz, we had that language, ANBM,
Yeah.
union with the previous language that we looked at.
Yes.
And it was said on the quiz that the union of these two languages, one that is regular and one that is not regular, should be, should be regular.
It is regular. The union is regular.
Sorry, I mean, this cell that you have right here on the slide?
Yes, this is regular.
This cell is regular, I know, but the other L, the other language we've seen.
Yeah, this is not regular.
With bigger or equal than, yeah, exactly.
Yeah.
The union of these two.
Yeah.
Is it regular?
Yeah. Yeah, it is. Yeah. It's regular because What's the union of the, what's the union of this language and this language?
I have an additional question related to this.
Okay, I just want him to answer the,
Okay, I'm sorry.
thank you.
It's not the universe, right? Because I could have BA.
What do you mean? But BA isn't here. BA belongs to sigma star.
Yeah, but in the union of sigma star with A and Bn. But if I'm considering only A and Bm union A and Bn, BA is not part of the universe.
Oh, okay. Well, that's not okay. So that's a different question. Okay, so it's A and Bn.
Yeah, that's what I was asking. It's from the quiz.
Okay. So he's probably gonna. Okay, I can do this, but he's probably gonna do this in lecture. This is a subset of this, right?
Yes.
Okay, so if I have A union B and B is a subset of A, then what is the result?
Okay,
Right.
go back to A.
Yeah, exactly.
So a not regular language can be within a regular language.
Yeah, actually, all non-regular languages are within a regular language. All non-regular languages are within sigma star.
Okay.
C'est bon? Or are you still confused?
No, it's good.
It's good? Okay. Yeah, there was another question? Or I already answered it?
You answered it. Essentially, you're saying that if, just to go back to your A union B is equal to A, if B is a subset of A.
Yeah, because imagine this, right?
Yeah. Okay, thank you. So
again, it is the first quiz, right? So don't try to get that discouraged because now you kind of know what the format is. So that's very, like the quizzes, the questions that you saw are very typical of the questions that are asked in 335 for tests and quizzes. So there's another question by Jolie. What about this question? Let L1 and L2 be any languages over the alphabet. Okay, so I guess I'm gonna scrap. I'm not gonna do these questions. I'm just answering the quiz questions. Yeah, so someone actually emailed me about that one. So I feel like it's because of how it was worded that a lot of people got confused. So you have L1 and L2 are any languages. Let's say over sigma AB, right? So it says if L1, L2 is equal to L2, then L2, so, okay, L1 is equal to lambda, the language containing lambda. So remember what this, if we go back to 232, what does this mean? It means if something, then this, right? And it's saying that this has to always be true. So L1 must always for any L1, right? It's let L1, L2 be any languages, right? So it's for any languages L1, L2. We know that L1 concat L2 is equal to L2. Then it must be always for any L1, L2 that L1 is equal to this, right? That, okay, is not true. Okay, why? Because again, let's use our famous one of our very useful languages, the empty set, right? If you take the empty set, L1 concat the empty set is the empty set, right? So L1, L2 is equal to L2, and now L1 can be anything, right? So it doesn't have to be this, okay? So it's just because I really feel like that's what most students thought of is it can be that, but really the statement is saying it must always be that, okay? That's why it's, what did I say? It's false. That's why it's false, okay? All right, so I guess I'm not going to do these questions. I can maybe, if you want, you could try these. And if you have any questions about them, because these are kind of similar to quiz questions as well, then you can let me know. Okay, so maybe any questions about anything else? Like the quiz or, well, I hope you don't have questions about the assignment because it's due in 15 minutes. I mean, I can still answer it, but, you know. No? Okay, so, all right, so remember the two questions that I asked you during the tutorial. I think they might be useful for you to think about. So which were they? The minimum and maximum number of states when converting an NFA with this number of symbols in the alphabet with this number of states to a DFA. So what's a min and max? And the other question that I thought was good was, if you have this guy, right, how can I easily reduce this NFA to have a smaller number of states? So someone did say eliminate the lambda. So I'm gonna push it even further after removing the lambda. Okay. So you can also think about that one. I think that one's good. And try to do, if you can, try to do these as an exercise. And if you have any questions about them, just let me know. Okay, so so take care, everyone. Have a nice lecture, and I'll see you Monday. Yes, Monday. All right. Goodbye, everyone.